I think we need to start the second talk for this session. The speaker is Simone Rota from CISA. He will tell us about the planar Abelian tools of 3D. Please take away.
Thank you very much, and thank you for the organizers, as always, for the opportunity to talk. So I would like to tell you a story that has been going on for a bit over 1 year, and this is in collaboration with a lot of people in the audience that you may know, Sergio, Sara, Riccardo, and as well as Anant and Gabriel, which are from CIS as well. And so this is a story about dualities, infrared dualities between three-dimensional theories. In particular, first I will discuss some dualities for n equals 2 QCD, and then I will describe some proposals for theories, for dualities between theories in the absence of supersymmetry. So of course, okay, I don't have to tell you that statements about infrared dualities are highly non-trivial. There are statements about, especially in 3D, there are always statements about strongly coupled, the strongly coupled physics of gauge theories. So it's, despite generally not providing a solution to a QFT, they still give us information, highly non-trivial information. And these infrared dualities are very common in supersymmetric theories. This is true in a variety of dimensions. In 3 dimensions, possibly the most influential and basic, I guess, one are mirror symmetry for n equals 4 theories. In particular, today I will mainly focus on mirror symmetry for n equals 4 QCD. And instead, halving the amount of supersymmetry, there is Aroni or Aroni-like dualities for n equals 2 SQCD. Now, a peculiarity of three-dimensional gauge theory is that there also have been many proposals in the context of non-supersymmetric theories. Many proposals of infrared duality starting from particle vortex duality, and then a large variety of generalization that generally go under the name of Bosinization dualities. So three-dimension really is a very nice playground to explore dualities, explore new dualities, but also given the amount of already known or proposed infrared dualities, is also an interesting place to study the interplay between them. And today we'll see a couple of stories in both directions. So the plan of the talk will be, roughly speaking, separated in 2 in terms of the decreasing amount of supersymmetry. We'll start with the 4 supercharges, n equals 2, and we'll propose some new infrared dualities for n equals 2 QCD. So this is the same amount of SUSY as the QCD that enjoy Aroni duality have, but they will have features that more closely resembles mirror symmetry. So this will be somehow a middle ground between these 2 fundamental dualities. And there is an additional, so what I mean by this is that across the duality, the flavor symmetries of one theory will be mapped to the topological symmetries of the other theory. And similarly, order operators, mesonic operators, will generally be mapped to monopole operators of the other theory. Another property that to me is quite striking is that while on one side I will consider n equals 2 SQCD, it's a non-Abelian gauge theory, on the other side, the other Lagrangian, which I will claim is dual to SQCD, is actually a fully Abelian theory. It's going to be an Abelian quiver theory with many U1 gauge groups, but they all will be Abelian. And then later in the second half of the talk, or the last 20 minutes or so, I will describe how this can be taken as an inspiration to instead propose some non-trivial infrared dualities in the absence of supersymmetry, in particular for bosonic QCD. So as usual, this usual picture of infrared dualities, this is what we'll be talking about. We'll have on the one side one Lagrangian theory, which will, for now, will be some three-dimensional QCD with the some amount of flavor and as well as some Chern-Simons level. On the other side, we'll have an Abelian quiver theory, and the claim will be that these two theories always flow to the same interacting conformal fixed point. So for today, I will mainly focus on the case where this theory actually flow to an interacting CFT. There are also interesting limiting cases where the infrared point is a TQFT, but for the sake of time today, I will not describe them. And as checks, as often happens, as checks of this duality, we can map the global symmetries, or at least the Cartan of the global symmetries of the two Lagrangians. We can work out a non-trivial map of BPS operators, which again, remind you, will involve regular operators on one side and monopole on the other side. While even though I will not give any explicit expressions or identities, actually the stronger checks that we are able to perform involve a supersymmetric localization, and in particular, supersymmetric partition function on the trisphere or squash trisphere, as well as the superconformal index. So I will not mention this too much, but keep in mind that in all the dualities, as long as we say in the supersymmetric realm, all the dualities that we'll discuss today, we are able to match at least to a certain level these supersymmetric partition functions. Okay, if there are any questions about the general idea. Okay, so I think especially for this audience, it's much clearer to directly present a sort of derivation of these dualities, as this will hopefully make a lot of properties quite apparent. So indeed, the derivation is essentially a study of mass deformations, of deformations of n equals 4 mirror pairs. In particular, we'll take n equals 4 QCD, and it's dual, which is, I guess, well known to all of you. And we studied deformations of this theory that break half of supersymmetry. If you're able to do this consistently on both sides of the duality, you do find a new duality now involving n equals 2 theories. Yes, I will only consider good theories. But later on, I will show you some additional techniques such that when you're already at the n equals 2 level, you can actually decrease the amount of flavor as much as you want. But the starting point will be good theories. Okay, so we studied with the mirror pairs, and now we want to break supersymmetry. There are many ways to do this. A lot of them are already discussed. But the way that we choose is through a real mass deformation. In particular, real mass deformation for a subgroup of the R symmetry. So the R symmetry is SU2H times SU2C, and we take the anti-diagonal combination of the Cartan, so U1H minus U1C, and we turn on a real mass for this symmetry. Which means that we turn on a background n equals 2 vector multiplet for this symmetry, and we give a web for the real scalar in the n equals 2 vector multiplet. This clearly breaks, well, it breaks a supersymmetry, R symmetry to U1, which is will be the commutant of this U1H minus C inside SU2 times SU2. And therefore it breaks supersymmetry from n equals 4 to n equals 2. Now, turning on this deformation is on the electric side is actually quite easily mapped to the other side, as real mass deformations only depend on the symmetries that can be defined just by knowing the symmetries of your theories. In particular here, knowing the map of R symmetry, which is what we care about in this instance, we can turn on a vector multiplet on the one side and correspondingly the same deformation on the other side. So the map of global symmetry across your initial dualities is already enough information to map the deformation. What will be tricky, and the reason why this all this story came up now, not 20 years ago, is that even in the presence of this deformation, there will be many vacua. Both the theories will have many vacua, and actually finding the correct mapping of vacuum under the deformation is the tricky part. Okay, so more precisely, we write the matter content in terms of n equals 2 supersymmetry of QCD. We have an adjoint chiral, and we have fundamentals and anti-fundamental chirals. Now, when we turn on the real mass deformation, all the fields that are charged under the symmetry, in this case U1H minus C, will take a mass. In this case, all of these fields are charged under this symmetry. So if you just turn on that, we will just gap the theory, we will give mass to everything, and we will flow to TQFT, which will be Chern-Simons UN at some level that depends on F and then. But we can do something a bit more refined. So we want to study the deformation, but we still want some interacting theory, some n equals 2 interacting theory. And this can be achieved by combining this real mass with a verb for the real scalar sigma. So we write the n equals 4 vector multiplet as n equals 2 vector multiplet times hyper, and the real scalar inside the n equals 2 vector multiplet takes a verb. And we can fine-tune this verb in such a way that the fundamental chirals remain massless. So we still end up integrating out the adjoint chiral and the anti-fundamentals, but we are left with some massless fields. It should be noted also that in order to actually solve the determinants equation, the one-loop corrected determinants equation, you should also turn on an FI deformation, which is similarly fine-tuned with respect to your real mass. Okay, so under this deformation, once we take the mass to infinity, the massive fields get integrated out, and in particular containing fermions, this will generate some Chern-Simons level for your gauge group. In particular, integrating out the adjoint chiral gives you a Chern-Simons level n for the SUM part of UN. So, okay, I should notice that being a UN gauge theory, you can actually define two Chern-Simons level, roughly speaking, one for the SUM part of the gauge group and one for the U1 part, and these are independent. There are some quantization conditions that should satisfy, but they can be independent. So integrating out the adjoint chiral only affects the Chern-Simons level of the SUM part, because the adjoint is not charged under the U1. While integrating out the F fundamental chirals gives you a Chern-Simons level for both the SUN and the U1 part. So at the end, what you find at the end of this flow is as an electric theory in your duality is n equals 2 QCD with the gauge group UN, this particular Chern-Simons level, which are fixed by the initial amount of fundamentals and the rank, and F massless fundamental chirals. Okay, so this is probably quite basic to a lot of you. I just wanted to point out that you can write down a real mass deformation that brings you from n equals 4 QCD to n equals 2 QCD. And now that you have all the details, especially the details about the fine-tuning of the real mass with respect to the Fi, you can try to map this on the mirror side and try to see what happens on the mirror side. So this is the situation right now. We have the real masses, and we can try to turn it on the mirror side. Again, for now, let me just focus on the fact that the mirror is, again, a non-abelian gauge theory. Actually, it has many non-abelian gauge groups. And again, we can turn on the real mass, but finding the correct vacuum is tricky. So what we did is, look very intensely at the equations of the vacuum equation, and also look at very intensely at supersymmetric partition function, and we came up with a proposal to what is the corresponding vacuum. And the proposal is the following. We propose that each non-abelian UK factor in the gauge group of the mirror is spontaneously broken to the maximal torus, U1 to the K. This happens via a joint Xing due to the real scalar sigma inside the n equals 2 vector multiplet. So more explicitly, given some factor inside the product group, we take the real scalar in its n equals 2 vector multiplet, and we give a vev, a non-homogeneous vev that breaks the gauge group in such a way. This happens for all of the gauge groups in the mirror. So at the end of the day, your resulting theory will be a fully abelian gauge theory, where you will have many U1 gauge groups, f-1 times s, U1 gauge groups, and each of these you can think of as coming from essentially the cartons of the original non-abelian gauge group of n equals 4 mirror symmetry.
Is there an intuitive way to understand why this specific vacuum is relevant with this increasing frequency partition?
That's a very good question. The answer is, the honest answer is no, at least to me. I don't have a physical intuition as to why this phenomenon takes place. So for now, you can take this as a technical result. So matching partition functions, this seems to be the vacuum. Well, this is a vacuum, this you can check, and this seems to be the vacuum that corresponds to n equals to QCD. I think it would be interesting to have a better understanding as to why we are now exploring some direction that seems somehow promising in terms of giving some physical intuition, but for now take it as a technical result. It's a technical result, but it's quite general, as I will try to show you. So this abilization feature will be actually quite general for many n equals to electric T. Yeah, the global symmetry will still be, up to discrete factor will be UF, or SUF times U1. You have a U1 topological and a SUF topological. And in the mirror side, I will describe it, you do have some non-trivial non-abelian enhancement of the symmetry, which follows the non-abelian enhancement of mirror symmetry of n equals 4 quiver.
All the symmetry will come from the topological symmetry.
You will have, so your symmetry on the QCD side will be U1 topological times SUF flavor. The SUF, or at least the cartandre of the SUF, will be mapped to topological symmetries in the quiver, and the U1 topological will be mapped to a regular flavor symmetry in the quiver. Yes. I'll discuss an example later, and there are ways that you can argue that non-abelian symmetry enhancement takes place. Okay, so this is the final proposal without the details. Again, to reiterate, we have here a non-abelian gauge theory, on the other side, a fully abelian gauge theory. And I should stress that the original input of all this analysis is just to study n equals 2 deformation of mirror symmetry. So on the left-hand side, we have some choices. We make a choice such that we get an interesting theory, QCD. What happens on the other side, the fact that the theory gets abelianized, is an output of the analysis, is an output of the computation. And again, as Chung pointed out, is an output that we don't fully understand. We don't fully understand why this is the case, but we understand it is a general feature, and we'll probably need some more thinking about. Okay, let's look at an example in excruciating details, but details are important. So we take the case of U2 with the 5 hypers. So here is standard n equals 2 quiver notation. I'm about to break supersymmetry to n equals 2. So an arrow is a chiral, a curly arrow is an adjoint chiral, and you have flavor groups and gauge gauge groups correspond to n equals 2 vector multiplets. So you have your deformation. On the left-hand side, as I said, they are joint chiral, and then the fundamentals get integrated out with this deformation. You're left with just the fundamentals, this arrow, and some Chern-Simons level that I will write in red. What happens on the other side? Well, the first thing that I said is that each gauge group is broken to the maximal torus. So the first gauge group, okay, the first gauge group just remains a U1, it's already U1. The second one is broken to U1 squared, and I draw it as a column-wise. The third one is as well similarly broken to U1 squared, and the last one remains a U1. Now what happens to the matter field? The adjoints get decomposed under the adjoint Xing. Of course, they become fundamental with respect to the Cartan. And most of them are massive, and we integrate it out. But some components of the adjoints remain massless. And in this case, for the first adjoint, only one component remains massless and becomes this vertical chiral. And similarly for the second gauge group. The bifundamental similarly get split into representation under the Xing. Again, some of them will be massive, and some of them will be massless. The massless one remain as chirals in the quiver, and are the ones shown here. And finally, very similarly to before, the flavor, well, half of the hyper is integrated out, and you're left with just one chiral. So this is the final theory in terms of matter content. Again, we integrated out a lot of fields, which include fermions. We got a chiral theory, and integrating out all the fermions generate Chern-Simons and mixed Chern-Simons terms for all the gauge fields. If you're careful about tracking which fermion is integrated out with positive or negative mass, you find these Chern-Simons levels. So again, red are Chern-Simons level for corresponding node. Green are mixed Chern-Simons level between two nodes. And it happens that you only have mixed Chern-Simons level between nodes that are connected by an arrow. That's an output. This is non-trivial. And so I will just denote them as a small number close to the corresponding arrow. So this is almost the final answer. What happens to the interaction? On the left-hand side, you have vanishing superpotential. On the right-hand side, you have two types of superpotential. First of all, you start with an n=4 theory, which has a cubic superpotential when written in terms of n=2. Some of these will remain. And I write it as W planar because it happens that the term involved in the superpotential are cubic terms, and they are cubic terms associated to each triangle, each face of the quiver. So for example, here we will have 4 superpotential terms inside W planar, one for each triangle, and they all will be cubic superpotential terms. But there's something more. Due to the adjoint Xing of the gauge groups, you develop a monopole superpotential. In this case, we had the 2 U2 gauge group broken to U1 squared each, and the breaking generates a monopole superpotential for each pair. So you have a monopole associated to this breaking, which is a monopole with genoflux plus under the top gauge node, and the opposite, minus under the top gauge node, and plus under this gauge node. And similarly, also here, you have another monopole with genoflux minus and plus. And this will be crucial to in order to match global symmetries of the theory. So that's the final answer. As advertised and promised, you get an abelian gauge theory, n=2 abelian gauge theory, where essentially the size of the quiver, as I'll show you later in the more general example, is related to both the rank and the number of flavors of your original theory. And the questions regarding this? Yes. Oh, this is similar to the Georgi Glashow model in 4D. So in a spontaneously broken gauge theories, you can have monopole operators, and okay, you can argue that there is a proliferation of monopole operators In the case of supersymmetric gauge theory, these appear as a superpotential interaction. This is essentially the Hafler-Garber-Witten phenomenon. And okay, from a posteriori point of view, as I show you from the matching of global symmetry, this is something that you might expect quite naturally. So there is nothing preventing these monopole operators to get generated. So if this is, we can discuss later. Okay, one property that may not be super apparent, but is true, is that, well, okay, this is n equals to theory. You have a lot of freedom in terms of interaction that you can have. But in this particular theories, and this will be true throughout the talk, all the Chern-Simons, mixed Chern-Simons, and superpotential interaction are actually completely fixed by the shape of the quiver. So the W planar, as I said, is related to the faces of the quiver. W monopole is related to, roughly speaking, the vertical arrows of the quiver. And Chern-Simons and mixed Chern-Simons also follow some simple rule. For the example that I showed today, the Chern-Simons will always be 1, and mixed Chern-Simons is either +1 or -1, depending on whether the arrow goes up or down, down or up. So this simplifies my life a lot because I don't have to give you all the information in all the diagrams. Indeed, everything is encoded in a quiver. All the gauge nodes are always abelian. All the interactions are completely fixed by some simple rules. And so actually the amount of data needed to define these quiver theories is very small compared to a generic n equals to quiver. So for the rest of the talk, I will just draw the shape of the quiver. Just keep in mind that at any point you can really write down all the relevant interactions. Okay, so everything is really encoded just in the shape. But for the sake of visual clarity, I will use this notation. Okay, so let's look at some checks of these dualities. First, of course, global symmetries. Now, this will not come as a surprise, as this really mimics the mapping of global symmetries across mirror symmetry for n equals 4, but it's nice to see the details. So on the left-hand side, again, up to discrete factors, symmetry is SU5 flavor, which rotates the 5 chirals, times U1 topological, and as I was discussing before, the mapping is that the Cartan of SU5, the maximal torus of SU5 is mapped to 4 topological symmetries, which are expected to enhance to SU5, while the one topological is mapped to some U1 regular mesonic symmetry, which is a symmetry that rotates the chiral up to, let's say, once you factor out gauge symmetries and superpotential terms. There is you're left with just one single U1 mesonic symmetry. Now, what happens for the topological symmetry? So you expect one topological symmetry for each gauge node, for each U1 gauge node, and you have 6, but you only expect 4. But this actually works out quite nicely because the monopole superpotential breaks a combination of topological symmetry. So in particular, I recall that you had one monopole superpotential with genoflux minus and plus. This breaks the anti-diagonal combination of the topological symmetries of this node and this node. So you're left with just one combination, which is a diagonal. And similarly for the second one. So you have you're left with just 4 topological symmetries, which are actually symmetry of the theories, each of which is associated to a column of the quiver. If you recall, each column came from a UN gauge node of the mirror symmetries or the mirror dual in n equals 4. So it makes sense now that each U1 topological symmetry is associated to a column. Then you have your mesonic symmetry, is already explained. One very nice thing that we can already get out from these dualities is the following. Now, on the right-hand side, there clearly is a mesonic operator that parameterizes a moduli space. Well, you can build many mesonic operators by contacting the fields, but turns out that all of them are identified between each other by the F terms due to the planar superpotential. And at the end of the day, up to F term, you only have one benzonic operator. So this gives you a prediction on the QCD, which is not readily apparent. This tells you that the QCD has a moduli space, a one complex dimensional moduli space, parameterized by some monopole. And this is highly non-trivial given the Chern-Simons level. But this can be checked, for example, by computation on the index, can be checked that there is some operator that you can identify as address monopole that at least at the level of computation that we're able to perform, does not satisfy, is not nilpotent, does not satisfy any non-trivial relation. And so you expect this to be, to parameterize a modular space. But again, all of this is quite explicit and simple on the Abelian dual side. Yeah, right. So the simplest check that you can do is to compute the index on the quiver side and see that it's compatible with the SU file. Now, from the point of n equals 2, this is what you can do. And you can also check that you do have BPS monopole operators that have the correct charges and spin to be conserved currents that enhance the symmetry. From the point of view of coming from n equals 4, we had, given the announcement of global symmetry in n equals 4, what we do is turn on a deformation that does not break the symmetry, and we go in a vacuum that does not spontaneously break the symmetry. So you do expect, so these are the 3 checks that we can do. Okay, some other questions regarding this example before? Yes. Yes, there is an additional step with respect to higher supersymmetry, which is F extremization in order to find the correct superconformal charge. But you, okay, at least numerically, we did check that there are monopoles with superconformal charge compatible with 2 that can be conserved currents, but it's not as it's not a proof. Okay, so let's move to the most more general case. Here we start with a good QCD with NEF and its mirror dual. And again, let's see what happens. On the left-hand side, as I told you a billion times by now, you get n equals 2 SQCD with some number of flavor and Chern-Simons fixed by n and f. And on the right-hand side, you get this monstrosity. But let's unpack it. So each node, each gauge node gets spontaneously get x to the maximal torus, and I write each cartan, each one as a node in a column. So the rank of the gauge node in the linear quiver becomes the height of the corresponding column in the planar side. So here you have increasing ranks, which gives you this sort of triangular shape because the height increases. Then you have a plateau, which is now a plateau in terms of height of the quiver, and then you get another triangle. By fundamentals, again, gets split into representation, and the massless ones are depicted as arrows. You get this so-like sequence of by fundamentals. And finally, the adjoint again gets split and gives rise to a sequence of n-1 vertical chiral fields. So, okay, that's the final answer. Again, you should be careful about Chern-Simons and mixed Chern-Simons interaction, but if you trust me, they will follow the same exact rules as the SU2 example that I showed before. So you will have planar superpotential. You will have now a lot of monopole superpotentials, one for each vertical arrow, and you will have Chern-Simons and mixed Chern-Simons terms. So now I just want to rewrite this in a nicer way. I just moved some of the nodes around. So the final answer for this particular type of QCD is that you get an infrared dual, which is essentially a shape of a rectangle. And now the parameters of your theory and f are mapped to the overall size of the quiver, while each gauge group is still a U1. Again, the feature of the duality are the same as the SU2 example. flavor symmetries, in this case SUF, are mapped to topological symmetries. So at least as far as the Cartan is concerned, here you have F minus one, F minus one columns, each of which will contribute as a U1 topological symmetry. This is after already identifying symmetries broken by the monopole superpotential. And again, the topological symmetry is mapped to the unique mesonic symmetry of the quiver. Again, for any n and f, it's an extremely good question. I will get to that in 10 minutes. It's not a symmetry, it's only duality. But yes. Okay, final comment about this. For any n and f, with this specific Chern-Simons level, this duality predicts that there will be a modular space of vacua, which again is a highly non-trivial statement and very hard to get out of the QCD directly. Okay, as Lama was spoiling before, there is a very interesting interplay between these dualities and Aroni duality. As I said at the beginning, we are studying n equals 2 SQCD with just fundamental, anti-fundamental flavor, well, in this case, only anti-fundamental, essential Simons level. These theories also enjoy Aroni, or more precisely, Aroni-like dualities. But they look very different, of course. These are dualities between two SQCD theories, while we have a duality between an SQCD and an abelian quiver. So, okay, in particular, we can look at an example. So we take UN with only 2n fundamentals. This is one of the theories for which we can build the planar abelian dual with the techniques that I showed before. And this is a particular analysis example because it enjoys something like a pseudo self-duality. So this is dual under Aroni-like duality to, again, UN, but with sign with 2n anti-fundamentals. I hope this reads. So these are fundamentals, and the other ones are anti-fundamental. So this is a non-trivial duality. Again, for both of these, we can construct a planar abelian dual. There is a slight technical point, as I showed before, due to coming from n equals 4. In the theories that I discussed before, you have differential Simons level for SUN and U1, but this can be tackled quite simply by a gauging and gauging procedure that we can do across the duality, which is essentially just a particular application of Witten's SL2Z action. Okay, this is just technical, but the quiver that we show now will be slightly different due to these intermediate steps. So again, let's take an example to be a bit concrete. So U2 with 4, this is our only dual to U2 with 4 anti-fundamentals. And now we can construct the abelian quiver. This is even simpler than the example that I showed. So here you will start from n equals 4 good SQCD with the 2n hypers, so the lowest amount of hypers possible to have a good theory. And what you get is this kind of quiver. And you may notice that the Chern-Simons and BF are slightly different due to this intermediate step. Okay, but now you can do something interesting. You can take this quiver and perform two local dualization. In this case, you just locally dualize this node and this node, so the left and the right gauge node. And okay, as always, assuming that local dualization actually give you new infrared dualities, what you find is this new quiver. So, okay, if you consider the node on the left, this is taken by itself, is just a U1, level 1, with one fundamental, one anti-fundamental. And this theory is technically given Kutuzov dual to U1 minus 1 with, again, one fundamental, one anti-fundamental, and a flip. This is standard cyber-like duality. You do this on for both nodes. You must be careful about also background Chern-Simons terms involving this duality. But what you find now, you can recognize actually as the planar abelian dual of the Aroni dual theory. So I started by integrating out all the fields from the n equals 4 QCD, maintaining only fundamentals. But of course, there is an analogous story with only anti-fundamentals. What you get will be something like this. So you get this nice commutative diagram of dualities. On top you have well-known Aroni duality, but instead of Aroni duality, you could instead chain this planar abelian dual that I'm proposing with local dualizations, again, using Aroni duality, but for U1 gauge groups, and again, planar abelian dual. So in some sense, you can think of Aroni duality as a combination of this planar abelian duality and local dualizations. You can generalize this to IN. I'm not drawing the quivers. It becomes a bit harder to read. But again, you can take two pseudo-self-dual Aroni theories, take the planar abelian dual. If you recall from the general story, you do have this kind of quiver for the pseudo-self-dual f equals to n, and the two sides are the same, so you get a square. So the theories here on the bottom left and bottom right will be like square-shaped quivers. And again, you can do a sequence of local dualization that connect the planar abelian duals of two Aroni duals theory. What becomes more complicated as you increase the rank is the number of local dualization that you do in order to connect these two theories. So all local dualization will still be quite simple. You have something like this, and you need also two additional duality that relate Aroni-like dualities that map some QD theory to another QD theory. But nothing more. You just need these three. And what becomes more complicated is the amount of times, the amount of steps that you have to do. So, okay, in general, this Aroni self-duality you can think of as a consequence of these planar abelian dualities. Okay. You can do still a bit more. These are just pseudo self-dualities, but actually there are, by now I would say, pretty standard techniques to essentially derive new, more general Aroni duality starting from the pseudo self-dual case. And these follow essentially the same pattern that we'll be following. You turn on a mass deformation, you map it across the duality, and you see what happens on both sides. So this I think started systematically in 2011, a paper by Benini, Cremonesi, and Closet. And we use similar techniques to actually show that starting from the pseudo self-dualities of before, you can actually, quote unquote, generate any type of Aroni dualities for UN with the fundamentals. So here you have now three parameters, n, k, and f. And again, you can think of these as consequences of your pseudo self-duality. So putting it all together, we have a nice sequence of implications. Again, the dualities that we described are mass deformations of mirror symmetry. So again, you can think of them as consequences of mirror symmetry. And again, you can perform a chain of dualities. So combining these planar abelian dualities with local dualities for U1 gauge groups to essentially derive, with the assumptions that I described before, derive Aroni duality. So if you put this all together, Aroni duality can be thought of as, at least in the case of UN with fundamentals, as a consequence of mirror symmetry. So this is one of the implications that I talked about at the beginning. So I have to point out that there is also an opposite implication that has already been discussed a lot in the literature, but essentially many people in this audience, so you know it probably better than me. But there is some sort of inverse implication that assuming Aroni duality and the application of local Aroni duality, you can derive, quote unquote, derive mirror symmetry. So we saw in the talk before by Chuang that there is a nice algorithmic way to produce mirror pairs. And another important factor is that the building blocks needed to perform the algorithmic approach can actually be, quote unquote, derived by applying local Aroni-like dualities. So I think this is very interesting. At the end of the day, even though these are supersymmetric theories, and we can perform many checks. Each infrared duality is still a conjecture. So I think it's very nice to find implications between different conjectures. Okay, the questions about this? Yes?
Depending on the value of k, in some cases it may have a massive monopole, which should be clear.
Yeah, very good. Yeah, skipped over it, but you're totally right. So the Aroni dual is qualitatively different, corresponding to these two regions in parameter space, and on the boundary of the region, so where f is equals to absolute value of k, you have one monopole that gets clipped. Okay, this we have not studied systematically, but looking at some example, this naturally comes out to the sequence of dualization. So in the slide before, if you try to do this in the case of so-called marginally chiral theories, you do the sequence of dualization, you do not find the planar Abelian dual of T2, you find this plus an additional singlet that now is a bifundamental because now the topological is mapped to, but you do see that here. Other questions? Okay, so let's see how much we can generalize this whole story. Well, first of all, we can consider theory with both fundamentals and anti-fundamentals. Now, actually, the technique is pretty similar to what we did up to this point, which can just consider a slightly different mass deformation from n equals 4 that preserves some, for some hyper you preserve the fundamental chiral, and for some other hyper you preserve the anti-fundamental chiral. And then the whole story goes very similarly. Of course, the result will be different. So in this case, okay, with this specific, with the flavor satisfying this bound, you do find again a large abelian quiver. Everything that I said before regarding this quiver still applies. All Chern-Simons monopole interaction, planar interaction are encoded in this quiver. But now, of course, we have a 3-parameter family of quivers, where the parameters are the two lengths and the height of the quiver. So you no longer have like a rectangular shape, you have this slightly different shape. Furthermore, we can generalize this to even different values of the Chern-Simons. So again, here the Chern-Simons was fixed by n and the total number of flavor because of the n equals 4 origin of these theories. But now that we have an n equals 2 duality, we can try to further mass deform this. So you can turn on a mass deformation for some of the fundamentals. And depending on the sign of the mass deformation, you will shift the Chern-Simons either up or down. And you reduce the number of fundamentals. If you do this, you're actually able to probe the full spectrum of n equals 2 SQCD theories. By this, I mean that you can probe this 4-parameter family of theories. The 4 parameters are the rank, the Chern-Simons, the number of fundamentals and anti-fundamentals, of course, with constraints on the quantization of the Chern-Simons server. And for all of these theories, well, all of these theories can be obtained as a mass deformation of one of these theories, possibly with higher rank and certainly with higher flavor. And following all this deformation on the planar side, on the abelian side, gives you an abelian dual for the resulting QCD. So the take-home point here is how general is this? Well, at the very least, for any n equals to UN QCD, you do have an abelian dual. And actually working out the exact shape of the dual is something that we're working on right now. Of course, the details can become quite intricate, but the main point stands. So this, I think, is extremely interesting. A very large variety of non-abelian gauge theories in 3D actually admit, if you're only concerned with the infrared behavior, they actually admit an abelian description. So of course it will be very nice to understand how general is this. Okay, so about to move to some non-supersymmetric theory. So if there are any questions about the whole talk up to now, this is a good point to stop me.
Any other model planar or say multi-planarizable.
Yes. Yes. So for example, linear chiral quivers, circular chiral quivers, USP SQCD. So there are a lot of additional examples that I will not presenting now that do admit a very similar dual descriptions. So they're always planar. Yes. Yes. I would say no. You may need some additional players in the game. So as you perform mass deformations, even in the case of QCD, you do find, for example, Chern-Simons levels between nodes that are not connected by some chiral. So the shape is a bit more general, but I would say that the parts of the quiver that it contains chiral fields, they're planar.
The other question is whether I'm trying to play with the two Chern-Simons levels of the U1 and the SU.
Yes.
Play the same game, but
Yeah. I lied a bit. I said that this is a 4-parameter family. It's a 5-parameter family. Indeed, you can generalize the level of the U1 inside the UN again by playing with Witten's SL2Z action, and this is actually quite straightforward to map across the duality. So for any value of the Chern-Simons of SUK and different value of U1, you can write down an Abelian dual.
and in those cases as well, you can basically explain, say, KSS dualities, ECC, all of that plethora.
No, as far as BCC dualities, for now we're only able to construct that commutative diagram in the absence of with only fundamentals. So there's still more to be done. And KSS we haven't even tried. But thank you. Okay. So of course, given this all these nice facts about QCD, it's natural to wonder, well, about SQCD, it's natural to wonder what happens to QCD without supersymmetry. Probably now actually performing a SUSY breaking deformation is not something that we have under control, but we can take these dualities as inspiration and try to understand whether there is some non-supersymmetric quote-unquote version of mirror symmetry or some non-supersymmetric duality that again resembles mirror symmetry. Now that we have these intermediate steps with n equals 2 supersymmetry, let's try to go even beyond. And this is what we do in the last paper that we publish again with the authors that I cited before. In particular, today I focus on QCD with some complex scalars, so bosonic QCD. And I will take a UN QCD, some Chern-Simons level K, F scalars with a quartic superpotential that preserves the SUF flavor symmetry. And for these theories, we give a proposal that's again an Abelian quiver dual, as you might expect, for essentially generic and F with some restriction on the Chern-Simons level. So in the case of n equals 1, this actually reduced to dualities that were already proposed. So let me review them quickly. So if you instead take a QED, let's start with QED. So we take QED with the sum amount of scalars, again with a quartic superpotential, quartic potential, and some Chern-Simons level. There has been a proposal by Kach and Tong, inspired by Abelian mirror symmetry. You may recognize the shape of this quiver. But now we have non-supersymmetric. On the left-hand side, you have bosons that I write with these blue arrows, while on the right-hand side, you still have quiver theory, a gauge theory with many U1 gauge groups, but now with fermions, which I write as a red arrow. And again, the number of nodes, as you expect, depends on the number of bosons on the QED side. And additionally, there is some further matter on the mirror side in the form of this real scalars sigma that only interacts with the rest of the theory with this Yukawa interaction. So there are various checks that one can perform, including mass deformations, phases of these theories. Again, there is a non-trivial statement about the enhancement of global symmetry. On the left-hand side, you have SU and S. On the right-hand side, you at most have U1 at the Lagrangian level. I will not review all of these, but let me just show a couple of interesting cases. If you just take U1 and S equals to 1 on the left-hand side, so you get a QED with one complex boson at level -1. On the right-hand side reduces to just a free-while fermion. So this is a well-known duality that was discussed way before 2016. QED with one complex scalar fermion, the Chern-Simons level, is dual to a free-while fermion. Of course, this is interesting because this is a solution of the theorem. No? On the left-hand side, you have some theory that flows to strong coupling. You don't really know how to solve it. It's QED in 3 dimensions. On the right-hand side, but the claim of the duality is that this is actually just equivalent to a free-while fermion. It's a free theory. It's a solved theory. You know everything about it. And you have a very interesting mapping of operators. The free-while fermion you can read from the QED side as a monopole dressed with the complex scalar. So the monopole itself is not gauge invariant due to the Chern-Simons level, but you can dress it with a complex scalar to make it gauge invariant. And the complex scalar on the monopole background has a spin a half mode. And so it's mapped to a fermion on the right-hand side. Okay, you can increase the flavor. If you take an S equals 2, now you have a duality between QED theories. This, of course, is not a longer solution. This is a duality between two theories that flow to strong coupling. And on the left-hand side, you have QED with two complex scalars, Chern-Simons level. And on the right-hand side, QED with two fermion. Again, with this additional real scalar and Yukawa interaction. Also, in this case, this we analyze in the paper, but I will not discuss it in details due to time constraints. Yeah. In this case, there's an interesting map of operators, and there is an interesting question about the announcement of symmetry, which again takes place here. So if you're interested in this and also some of this deformation, ask me later. But okay, now that we reviewed some of the essentially known dualities, let's move to non-abelian. So let's move to QCD. So as you might expect, this is the proposal. So on the left-hand side, we take some QCD with some number of complex scalars. And again, I'm not writing it explicitly, but you have a quartic potential and some specific Chern-Simons level. And the proposal is that this theory is infrared dual to this quiver theory. This is, of course, very similar to what we saw in the supersymmetric case. And now you have both fermions and scalars in this theory. And again, you have some cubic Yukawa interaction corresponding to the triangles. You again expect some monopole interaction associated to the vertical lines. And again, you have some additional real scalar sigma that I'm not writing explicitly. So let's see some properties. Again, flavor symmetries are mapped to topological symmetries. And I'll discuss later what in a second, what are the operators that you expect to actually implement the enhancement of the topological symmetry to SU5. And again, mesonic operator would generally be mapped to dress monopole operators and vice versa. So as an example, we can take some mesons on the left-hand side, phi star phi, and try to find operators in the quiver dual that have the correct charges to be the corresponding operators. So for example, So for example, phi 1 star phi 2, we claim, or well, let's say it has the correct charges to be mapped to this particular monopole. So here the notation is just, here I put the genofluxes of the monopole with respect to the nodes of the quiver. So this is the shape of the quiver. This monopole has genoflux 1 under this node and nothing else. And can be made gauge invariant by dressing with two fermions. And if you compute these quantum numbers as the correct quantum numbers to be mapped to this. And you can find monopoles with the correct properties to be mapped to all the off-diagonal mesons of the left theory. All right. Perhaps more interestingly, you can also study operators that may enhance the symmetry to SU5. This is part of the claim of the duality. In this case, you find very similar monopoles to what I showed before. Indeed, the picture has not changed. The difference is that now we address these monopoles with the spin 1 modes of the fermion in the monopole background. So we get a spin 1 operator. The fact that the genoflux are the same is essentially given by the fact that both the mesons and the conserved charges are in the adjoint of SU5. Am I doing with time? Oh, perfect. Again, in this case, the claim following from the n equals 2 case is that these particular monopole operators, which are spin one operators with in the adjoint of SU5, enhance the global symmetry from U1 to SU5. Although in this case, of course, computing the conformal dimension of this monopole operator is not entirely feasible. Although, okay. It might be interesting, at least in some large enough limit, to look at this more carefully. But it's still highly non-trivial that you do find some operator that at the very least have the correct charges. So, for example, if you consider some different proposal, this will change drastically. So again, this was a proposal for QED with 5 bosons. You can think of this generalization of n equals 2 SQED with 5 chirals, where we only keep the boson inside the chiral, but we can do something more general. We can take the bosons inside 2 of the chirals and the fermion inside the other chiral. And even in this case, we propose this Abelian dual. This is a peculiar case where the dual is fully bosonic. And again, in this case, well, you have 3 different types of mesonic operator because you have scalars and fermions, and these will have different properties, different spin and charges under the U2 times U3 global symmetry. And again, you can consider monopole operators very similarly to before, but now all the details will matter. All the details will matter. For example, if you consider mesonic operators, these are mapped to some monopole operators dressed in a particular way such that the spin is integer. While, and similarly for purely fermionic mesonic operator. While for mixed operators, again, you can find some monopole with the correct charge under the global symmetry and show that, for example, their spin is half integers, as you expect. So, okay, I think it's time to wrap it up. Again, these were examples. Here I did not put the most general proposal. If you're interested, please either feel free to either ask me or look at the paper. Okay, some future direction. Starting from the back, I showed you some proposal for a duality for QCD with fermions, and I lied to you a little bit. This proposal actually seemed to work out only if you have enough bosons, at least as far as we understand now. So first of all, it's interesting to ask whether this is a technical issue or there's something deeper, and how much can we extend this proposal and have a self-consistent picture. And then, of course, aside from proposals itself, it would be interesting to actually exploit these dualities, similarly to what we did in n equals 2, to understand properties of the QCD. So, for example, it's not known, it's not known for which amount of matter content QCD actually flow to conform a fixed point, or when they have more complicated phase diagrams, and a good dual frame may be able to answer some of these questions. Going back to n=2 gauge theories, as I tried to answer to Mark before, we have a large variety of theories with the abelian gauge group that are dual, non-abelian gauge group that are dual to abelian gauge groups. Here is a list of other theories that I did not present to you today explicitly. So it's natural to ask how general is this? Can you find the theories that do not admit such an abelian dual? Or on the other hand, is there a way to describe every non-abelian gauge theory, at least with n=2 supersymmetry, instead in terms of an abelian dual? And finally, which is something that we're working on right now actively, I show you a nice interplay between, well, mirror symmetry and harmonic duality, more precisely between these abelian planar duals and harmonic duality. But there are a lot of details that are still missing. So, for example, the cases where of QCD with both fundamentals and anti-fundamentals is still something where we cannot draw the full commutative diagram. And of course, it will be nice to close that up. So thank you very much for the attention. If you have questions.
Can you put this, those supersymmetric version about your list using the planar those supersymmetric planar version?
Sorry, second.
So as you did in n=2k, can you also prove some? There are many known examples of those.
Yes. No. Unfortunately for now, the restrictions on the number of bosons and fermions under which we can find some consistent dual are incompatible with instead the restriction for which some bosonization dual, QCD to QCD dual has been proposed. So the two.
Then can you use your picture to propose some new?
It's a good question. Up to now, I don't know, but yeah, maybe we can discuss later. But yeah, the whole business of local dualizations is a bit trickier, of course.